Module 4, Lesson 5 deals with scientific notation. The suggested pacing says this is going to be a 90-minute lesson, and the content objective says students will write numbers in scientific notation. I don't have a clue how this lesson could take 90 minutes, but you know, your textbook has a way of really milking things out, so let's see how well they milk this one and see if they can get their full 90 minutes worth out of it. When representing numbers in scientific notation, how do you know if the exponent on the power of 10 is going to be a positive or a negative? Well, let's see here. Let me zoom down just a little bit. We've got scientific notation, and it says what is used to write very large or very small numbers. I used to say for really big numbers or wee little tiny numbers. The parts 7 and 7/75 times 10 to the 6, the 7 and 7/75, that's going to be a number greater than or equal to 1 but less than 10. So you see right here, you can have anything between 1 and 10 in the first spot. You have 2 decimal places after it, and then times, the power always going to be raised to the power of 10, and then you have the exponent going on from there. And then the y. Well, let's see here. Archimedes was a brilliant Greek inventor and mathematician who studied the Egyptian city of Alexandria, the center of then it was the center of the scientific world. Archimedes used his knowledge of mathematics to attempt to calculate the number of grains of sand in the universe. Okay, think about this for a minute. He wanted to calculate how many grains of sand there would be in the universe. Archimedes had way too much time on his hand. Archimedes introduced a new classification of numbers to do this, and we'll talk about that in just a second. Alright, I'm back. The first order, numbers went from 10,000 up to 10,000 times 10,000, also known as 100 million, which is also known as 10 to the 8th power. His second order was 100 million times 100 million, also known as 10 to the 8th times 10 to the 8th, or 10 to the 8th squared, which would be 10 to the 16th power. Third order went up 10 to the 8th times 10 to the 8th and times 10 to the 8th, and so on, and that's how his orders went. Now, to calculate the numbers of grains of sand that fit in the universe, I guess he didn't realize at that point that the universe never really stopped. It goes on and on forever. He needed to use numbers up to the 8th order, which is going to be 10 to the 8th times 8, otherwise known as 10 to the 64th power, which is all of those zeros. Would you really want to have to write all of those zeros, or would you want to write 10 to the 64th power? That's the whole point of scientific notation and using exponential notation. Now, by the way, Archimedes, he lived a long time ago. He's dead now. He says he was of Syracuse in the time of 287 to 212 BC. And yes, I know it looks like it's backwards. That's because it's BC, which, depending on your philosophy, is either before Christ or before Common Era. And anything before in the BC, it counts backwards. Archimedes didn't stop there. He went on to write even larger numbers. He logically continued until he reached what he referred to some as Archimedes' beast number, which was 10 to the 8th times 10 to the 8th, raised to 10 to the 8th, raised to 10 to the 8th again, and it is equal to the number 1 followed by 80 quadrillion zeros. It is too big for any modern calculations. Yes, why would you want to do this? I have no idea. So, how are we going to work on this? We'll find out in just a second. So what we have here is the number 819 million, and we want to write that in scientific notation. Your decimal, it's located at the very end on the right, and we're going to move the decimal to where it falls directly after your first non-zero number. In that case, it's going to be the 8. And how many times did you bounce it? 1, 2, 3, 4, 5, 6, 7, 8. So that's how many bounces you have. And then from there, literally all you have to do is take those first three numbers with a decimal in between the 8 and the 1, write times 10 to how many times did you bounce a decimal? You bounce the decimal 8 times, and that gives you this number here written in scientific notation. That is your 90-minute lesson brought down into about 30 seconds. Now let's see from here. To multiply it by power of 10, the exponent will be the number of places the exponent is moved. So if you could take and write this as 8.19 times 10 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 times 10, that is how you would actually write that out if you wanted to run it all the way out into expanded form. When working with very small numbers, the process is going to be the same. So here we have a wee little bitty number where you've got the 0.1, 2, 3, 4, 5, 6, 7, 8, 9, and I'm not going to try and read that one properly. And you still bounce that decimal to go in between or directly after your first non-zero number, which is the 8. Here they bounced it 7 times. So now you have 8.19 times 10 to. Now this is a wee little bitty number, so that means your exponents can be a negative version of how many times you bounced it. That's a couple quick skinnies on how to work with scientific notation, but we're still not done discussing the concept. So now that we understand kind of sort of how it all works, where would you really use this? Well, say you wanted to measure the mass of an electron. It would be this number times 10 to the negative 31 kilograms. We're talking a really, really tiny little number, all right? That means that if you were to write that as a decimal, you bounce that decimal back here 31 times before you were done. Scientific notation is called standard form in Britain. That's interesting because it's the opposite here. Standard form here is going to be the normal way of writing the numbers. The approximate number of cells in the body is going to be 1 times 10 to the 14th power. Okay. The distance between the Earth and the Moon is going to be 2.5 times 10 to the 5th miles. And the distance between the Earth and the Sun is going to be 9.3 times 10 to the 7th miles. Different uses of scientific notation. The approximate speed of light is going to be 1.08 times 10 to the 9th kilometers per hour. The population of the world is 7 times 10 to the 9th people, and the surface area of water on Earth is going to be 1.4 times 10 to the 8th square miles. And with that, we are about 8.5 minutes into this lesson, and we still haven't actually started applying it to anything worthwhile. But now we at least have a good solid foundation on the history of scientific notation and how it could be used. Our introductory question says, how can you write a very large number or very small numbers in different ways? Let me guess, scientific notation. The Earth is the third planet from the Sun in our solar system. Because the Earth's rotation around the Sun is not circular, it is going to be about 95 million miles. And the minimum distance is going to be about 91 million miles. So apparently there's times when we're closer to the Sun, and there's times when we're further than the Sun. I really didn't know that. Consider the minimum distance of 91 million miles. How many different ways can you think of to write this? How could you write these numbers as a product of 91 and another number? In other words, 91 times 10 raised to a certain power, otherwise known as scientific notation. These are some of the things we're going to be learning how to do in this lesson. So if we were to try to write 91 million as a product of 10, well, from there we would start off by acknowledging the fact that 91 million is the same thing as saying 91 times 1 million. All right, we can do that. And then we could say from there, well, how many tens is it going to take to make 1 million? And you can see that you would end up with, well, if you bounce your decimals a little at a time, 91 million would times 10 to the 0th power, well, that'd be equal to 1. That means you'd end up having 91 million there. However, if you were to take and do 10 to the first power, your decimal would move over 1, and so on, and so on, and so on, until you got down to the scientific notation version of 9.1, where the decimal was directly after your first non-zero number times 10 to the 7th. So that would be the scientific notation version of how to explain the distance between the Earth and the Sun at its closest point. Now that table is kind of boring, and I'm not going to make you do all that kind of work to show your answers. I am going to show you some pretty cool stuff on doing it a lot easier. Now, it says, did you choose to represent 91 million as either this number or this number? And if not, can you explain why? We're just going to skip over that because this is really boring me now. Now we're going to skip over a whole bunch of that stuff because it is just fluff and it's only going to lead to confusion for you. And we're going to take and start now with some really good meaty stuff, including standard form is one of your definitions, which says numbers that do not contain exponents are written in standard form. However, when you work with very large or very small numbers, it can be difficult to track place value, and scientific notation is going to be a way of writing very large or very small numbers. From here in words, we can take and say the scientific notation is a way of expressing a number as a product of a factor and an integer power of 10. When the number is positive, the factor must be greater than or equal to 1 and less than 10. Well, all those words are pretty darn confusing. But in symbols, well, we're getting a little better here. For positive numbers, when written in scientific notation, it is going to be written as a times 10 to the nth power, where a is going to be greater than 1 or equal to 1, but less than 10, and n is going to be an integer. Well, that's a little better, but still kind of confusing, so let's take and put this simple. 425 million, we took the decimal, moved it between the first and second non-zero number, which gave you 4.25 times 10 to the 8th. Here you got 3, let's see, that's tenths, hundredths, thousandths, 10,000ths, millionths, so that's 3 millionth. That would be 3, the decimal's right there, invisible after it, times 10 to the negative 5th. Now that's a quick skinny. We're still going to teach you more, so hold on. Quick look at these 4 numbers. Wants to know whether or not they're listed in scientific notation. Where's your decimal at? Well, your A value is going to be 10, which is going to mean that that is a no, because your A value has to be less than 10 or greater than or equal to 1. Here your A value is just 2. That's less than 10 but greater than or equal to 1. That's going to be a yes. Here your A value is 9.5. That's less than 10 and greater than or equal to 1. And here you have 526 thousandths. That is less than 1, so that one's going to be a no. Check your answers. All those check. An easier way to look at it is where's your decimal. If your decimal is anywhere other than directly after your first non-zero digit, it is not going to be written in scientific notation. And now we're finally getting into the meat of the lesson, where they're giving us some solid examples, and hopefully they show us a good way to do it. Write 5.34 times 10 to the 4th in standard form. Remember, standard form says there's not going to be any exponents involved in it. So when we work through this, looks like they're going to give us method 1. Method 1 says to write it as the power as a product. So here you have 5.34 times 10 to the 4th. That means you have 5.34 times 10, 1, 2, 3, 4 times, otherwise known as 10 to the 4th, where 10 to the 4th, that's going to be 10,000. How many zeros? 1, 2, 3, 4. How many zeros? 1, 2, 3, 4. Interesting. And then from there, when you multiply that times 5.34, you get 53,400, which is going to be your final answer that you can type in there if it makes your heart feel all warm and fuzzy and stuff. Now that is a perfectly good way of doing it, and it does explain why it is what it is, how the numbers work to get down here, but it's not really the way most of us use. Most of us do this by simply moving the decimal point. So here we've got 5.34 times 10 to the fourth, and watch a little video they're doing. They're going to do it again here. There it goes. There's your comma. Now they're going to start off with your decimal, which is directly after the 5. So there you go. Right here, they're going to move it 1, 2, 3, very slow bounce, 4. They're going to annex in zeros as needed, and then now they're going to take and put the comma where it belongs. It really is that simple. So anytime you're multiplying by 10 to the fourth, all you have to do is go 1, 2, 3, 4. See, mine's a lot quicker than theirs. Annex zeros, put in your comma, you're done. It's that simple. So which one of those methods do you like the best? Me? I'm all about doing method 2, but I'm also all about showing my work on method 2. So whenever you do this example, if you choose to use method 2, make sure you're giving me bloop, 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 where you're bouncing those decimals as you move it over to solve the problem. Go. So are you ready to see how I would show my work on this one? I would start with a 7.42. I acknowledge the fact I'm moving the decimal 5 places. It's positive, so we're moving to the right. We're going to talk more about that later. So I'm going to go 1, 2, 3, 4, 5. And I'm going to annex zeros as needed. From there, I'm going to rewrite that number, 742, with 3 zeros after it. And I'm going to put my comma in where it belongs. 742,000 is my final answer. Come over here, 742, comma, 1, 2, 3. Let's see if they allow that comma. They do allow the comma. Answer checks. It really is that easy. Come back and watch part 2 of this fun little video series on scientific notation.